Hey guys, today we are talking about our Unit 4 momentum review. Sort of just some common questions, some misconceptions that we've been seeing throughout the unit, stuff I just want to make sure you understand and feel comfortable with when we get to test day. So, first question is it possible to have two objects that are moving, but when added together, they have a total momentum of 0? So that is our first question, and the answer is yes, that's absolutely possible. And it's because if they are moving in opposite directions, that means one is positive, one is negative. That means total they're going to end up equaling 0, even if they are both still moving. Our example is a gun being fired. A lot of our explosion type problems have this concept of, hey, that we have a velocity or total momentum of these objects being 0. And remember that momentum before has to equal momentum after, so it's not moving before. So added together, the momentums also still have to be 0. So we would then have the gun moving to the left, the bullet moving to the right, and that would end up causing when you added those together, that would still be 0. So the answer is yes, you can absolutely have that as long as they are moving in opposite directions. All right. So this one is talking about Cassidy, and she's driving her car at 15 miles per hour, or meters per second, my bad. When she sees traffic ahead and brakes, it slows down to 3 meters per second. What was the change in momentum for her car, and what was the impulse exerted on her car? And the question we're really asking you is, what is the difference between question A and question B? And your answer should be, there is nothing different, guys, nothing different. Remember, impulse, by definition, is just a change in momentum. When we talk about impulse, we're talking about how an object's momentum changes. So therefore, this one where it says, what is the change in momentum? What is her impulse? They're the exact same question, the exact same thing, because impulse means change in momentum. So that is not any different. Now, this one is a scenario we've done a few times, or at least different variations of this, and we're comparing what happens to force, time, and impulse in both scenarios. So we have a car running into a haystack and stopping, and then a car running into a brick wall and stopping. So what happens to force? We're going to compare force, time, and impulse in both scenarios. Now, when it runs into the haystack, it means that it has a smaller time. And then by result, if you're having a smaller time, that means the collision is going to be longer. For the brick wall, it is greater because it hits you all at one shot, which means that our time is smaller, but that means force is greater. The impulse is the exact same in both scenarios because we just talked about it. Hey, if this object is changing its momentum, in scenario 1, it comes to a stop. In scenario B, it comes to a stop. So the impulse is the same in both, even though one has a greater force, one has a greater time. Now, this is a similar sort of building off the same idea. Which scenario is more dangerous to the driver? In scenario A, a car experiences an impulse of 30,000 kilogram meters per second and a force of 1,000 newtons, or a car experience is an impulse of 10,000 kilogram meters per second, but a force of 20,000 newtons. So which do you think is a more dangerous to the driver, scenario A or scenario B? And our answer is scenario B. It's not an impulse that causes damage in a crash. It's the force, right? The more force the object feels, that is what ends up destroying the car, or if we're talking about a car, or applying a bigger force, right? You can go from 100 miles per hour in 30 seconds. That's really not dangerous at all. That's you just sort of slamming on your brakes for 30 seconds, right? That would take you probably that time. And that's significantly safer than 35 miles per hour and running into some sort of wall or object, right? That is one has significantly more bigger impulse, but the other one has a bigger change in how much force the object feels. So that is what ends up being the same. So the answer is, doesn't really matter how high your impulse is. It's the force that's going to end up causing damage. Now, remember, what is the law of conservation of momentum and when does it not work? So we're asking, when does the conservation of momentum not work. If you forget what the law of conservation of momentum is, remember that means when we're talking about, hey, momentum at the start of our problem has to equal the momentum at the end of the problem. So, or the momentum in equals the momentum out, whatever the start versus the end. And when does it not work? The only time it doesn't work is when there's some other outside force taken into consideration. A lot of times we have friction as our examples, right? If we're talking about like an explosion problem, we have an object that is thrown in space. They're going to just, one object will move this way, one object will move that way, and that is never going to stop. But the reason it does stop on Earth is because we have friction always. So the only time this is not true is when there's some sort of outside force, and normally you would take that into consideration when we're doing all of these problems. So this one, what happens to impulse if my time doubles? So we're trying to think about, hey, if I do something to one side of my equation or do something to, how will it affect something else? So what happens to my impulse if my time doubles? So it would double, right? That's pretty easy. Whatever you do to one side of the equation, you have to do to the other. That is always going to be true. So here we just sort of did it. I'm going to plug in ones for these examples. So in this first scenario, we have an impulse and we do force times time. And we're plugging in 1 for everything. So we have 1 times 1, and that gives me an impulse of 1. Now, what would happen if we doubled time? Impulse equals force times time. And instead of, we have 1 times 2, and that gives me an impulse of 2. So because impulse and force and time are on different parts of our equation, that is why we end up getting that answer of our impulse doubled there. Now, this is a similar type problem, but now we're talking about momentum. So what would happen to my velocity if my mass doubles, but my momentum stays the same? So if you all remember, you guys will always have your equations when this comes test time. So you would look at the equation and we would say it would end up being cut in half. And you could prove this mathematically again. I'm going to just plug in all of my numbers. So we don't know what V is, but I'm going to plug in 1 for everything else. So I have momentum equaling 1, I have mass equaling 1, and then times V. This is the wrong unit. That is meters per second. For velocity, that would be a -1 for Mr. Wister. So don't do that. Remember, velocity is measured in meters per second. Now, if we double mass, what would happen to, but keep the momentum the same? That was our requirements. So we have momentum is 1 equals 2 times V. And we are looking, and then once you move that over, it ends up cutting our velocity in half. And then there I have the right unit, right? So if you guys see something like this, something similar to this, remember, I think the easiest way is to write down your equation and be like, hey, if I do this to one side, I like to plug in ones. If you guys want to think about it as like, hey, whatever I do to one side of the equation, you're going to end up doing it to the other. Or in this case, if we're keeping this side the same and I move this up, the only way that could be true is this one counterbalances it and gives us that 1/2. Now, if you forget, remember, we're talking some of our math. We did 3 different types of collisions. And the most important thing is identifying them. That's where people lose points, is when you say, hey, I think this is a collision that is an explosion type and it ends up being elastic. That's where you're going to lose your points. If you forget your 3 equations or 3 types of problems, it is elastic, inelastic, and explosion. Here's how I identify them. By definitions, right, I give you that, but I also sort of think of it's important to look at it like, hey, I have how many objects to start and then how many objects to finish. So elastic collision is colliding objects that rebound. They are 2 objects to start, and then at the end of the collision, they are still 2 objects. So that is an elastic. Inelastics are objects that stick together. A lot of times it'll say they are stuck, they combine, something like along those lines. And that's 2 objects at the start, but at the end, it's only 1 object. So that's the difference between elastic and inelastic. An explosion type problem is a single object that's going to be split into multiple objects. A lot of times we just split them into 2. That's the gun example we just did earlier in this video. And then so it's a single object that's being split in 1. So we have 1 at the start, and then at the end, it's going to be 2. Often they're going in opposite directions. And lastly, this is not really a question as much as it is super duper important. Take the time to write this down right now. This is your units. I made a unit mistake because they are easy to make, guys, but you got to just make sure you take your time when you do this. Write everything down. mass equals kilograms, velocity is meters per second. Your impulse and momentum, remember, impulse is just a change in momentum, so that's going to give you the same unit there, is kilogram meters per second. Force equals newtons, and I don't know if you could see that last one on my screen. There it is. Time is obviously in seconds, so that is not that new. So that is pretty much some common questions, some misconceptions that we've gone over, that we've seen, and I'm hoping that helps you guys out for your review.